Hello friends, in this video, let's have a look at problem 2957. Remove adjacent almost equal characters. Actually, in this video, we're going to explain a solution based on break the string into chains. The time complexity will be O of n. Actually, this problem is rather straightforward if you realize the recipe. So first, I'm going to digest the requirement, then we do the analysis, and finally we do the code. So here we are given a string called word, and in one operation, we can pick any index I of word and change word I to any lowercase English letters. So this is the operation we can take, right? So we want to find the minimum number of operations needed to remove all adjacent, almost equal characters from word. So here, almost equal means adjacent in the alphabet. So we can think of the two characters either equal or just adjacent, like B, C, or A, B, right? So here, let's look at example 1. So here we get 2, right? So you can modify the A at index 1 and the A at index 3, right? So here, if you look at example 2, so for example, AB, you should modify 1. Similarly, DDE, we can modify the middle D, right? So this is the 2. So in example 3, so we have XYZ, Y, X, ZY. So the length of this guy is 7. So we return 3. So we'll explain why we return 3. So here the constraints are the following. First, the length of this word can be is bounded above by 100. So this number is rather small, right? So word consists only of lowercase English letters. So that's the main problem statement. So here, let me write some strategy, so then we explain it. The strategy would be break the string of word into maximal chains. So such that in the chain, so the near adjacent characters are adjacent or almost equal. So the main observation is the following. So given a chain, right, of length m, right? So here the chain is almost equal. So which means that so each adjacent indices correspond to almost equal characters, right? Then the number of operations needed is nothing but m over 2. So here over is integer division. Then we just need to break the word or the string into maximal chains and then compute this quantity and sum them together. So here, let me explain why. So I hope that you can have the intuition after our explanation. The reason is that if we consider two characters, so there's just two positions, or if you consider length 3 strings, so we consider the first one and the third one. So in between, we can tune it so that the 3 are not almost equal. The reason is that we look at most, we can look at two positions, right? But there are 26 lowercase English letters. So in other words, we have large room to make them non-equal or almost equal. So this is the main intuition that is at the hood in solving this problem. So here, actually, we can use example 1 to demonstrate the problem. So here, if you have AA, right, you need to modify one of the A. So the operation needed is 1. So if you have 3 A's, you just need to modify the middle one. So this is 1. Similarly, if you have ABA, you need to modify anyway, right? So we modify the middle one, that is 1. So now if you have 4 A's, you need to modify 2, right? You modify either this one and this one, or this one the first one, the third one. Anyways, you need 2 operations because 1 operation is not not sufficient. So similarly, you can modify B or A, anything, but we just need 2. So if you have 5 A's, as in example 1, so you're going to need 2. So you need to modify the A at index 1 and the A at index 3, right? So you can see this is hold for any chains, right? As long as the adjacent are just nearby or almost equal. Then if you look at 6, right? 6 A's, so you're going to need 3, right? So now if you look at 7 A's, right? As you are going to need 3 again. But if you have 8 A's, you are going to need 4, right? So now if you look at example 3, so here you have x, y, z, x, y, z. So this is the maximal chain, right? Because adjacent characters just almost equal. Then the length is 7, so 7 over 2. So it's less than but 3, right? That's why we need 3. This is also the output for this one. So with that said, basically writing the code is a breeze. Now let's look at the code. So first, let me see. Let's write the length. This is just for convenience, right? So now I can initialize a result variable. So we're going to return its final state after we break the word into chains. So here by break, we just break in the air, right? We don't need the specific pieces. So we can start from the first one. So the current length, let's say, is 1. Let me use this segment length. So it's 1, right? Then we're going to iterate for I in range, so 1 up to n. So here the segment 1 means that we consider the first character, right? So now let's check if the ordinal number of the current character and the ordinal number of the previous one. So here, because I start from 1, so I minus 1 makes sense, right? Then we'll consider the absolute value, right? If the absolute value is less than 2, which tells that the two words, the 2 characters are almost equal, right? In this case, so we are going to increment the segment length by 1. So in general, so if it's not, right, so we are going to reset this segment length. So we're going to reset it to be 1. But we need to collect this kind of quantity, that is a length over 2. So here, in general, if in the process of incrementing, we don't do this m over 2. But one special case is if I equals n minus 1. In other words, we already arrived at the end, so we're going to do this, right? So that is segment length over 2. This is the one. And another one is that each time we are going to reset, so we need to do this increment. So let me put it here. So now we have the full logic. Now we just need to return the result. So this actually completes the coding. Now let's do a test. Yeah, it passes one example. I guess this is example 2. So now let's look at the generic case. Yeah, it passes all the cases. So with that said, basically I feel that for this problem, so almost equal, just add a little bit layer to this problem. You can think, oh, if we require they are the same, then we just need to break the pieces like this, right? Consecutive pieces, and then summation the length over 2. But here, the same, because if it's adjacent, so you just need to do the same change as like they are the same, right? So then why we can do this, or we can solve using this kind of thought process, is due to the fact of difference in degrees of freedom, right? So you see length 3, 1. So if I want to make them not almost equal, I just need to modify the middle one. But the 2 sides just have 2 positions, fixed positions, right? And then we have 26 characters. So we can't just choose one far from the two, right? So this is the main logic. So with that said, that's basically the overall logic. But if you think of the time complexity, I don't think we need to explain too much, because we just do a linear scan, right? Then each time we look at character, so we get the segment, and then we do the summation. So it's O of n, where n is the length of the string word. So with that said, I guess that's about it for this specific problem. Actually, it's good to practice the thought process or practice similar problem. For example, if you see if there are some similar questions, minimum changes to make alternating binary string, right? So with that said, I guess that's it for this video. Thank you.